So let's look at these two simple and familiar examples together. We have the alternating harmonic and the alternating series of reciprocals of squares of positive integers. We know very well that both series converge by the alternating series test, but the first series is not absolutely convergent because the series of absolute values is the harmonic series, which we know very well that it diverges. So we say that the first series is conditionally convergent, and while the second series is absolutely convergent because sigma 1 over n squared converges. So now this is an important this distinction between the two, because conditionally convergent series and absolutely convergent series behave very differently, as we will try to understand here. So if we start with a general series sigma an probably with mixed positive and negative terms, doesn't have to be alternating. We can define two series from sigma an as follows. The first series will have terms Pn, and Pn is defined to be, we define it to be absolute An plus An over 2, and Qn will define it to be absolute An minus An over 2. So we probably will see what's happening. If An is positive, absolute An will equals An, and Pn will give you just An, and Qn will return 0. And if a certain term of a series An is negative, then Pn is going to be 0 and Qn will be negative An. So we can think of Pn as picking, or sigma Pn as picking the positive terms of the series sigma An, and sigma Qn picking the negative terms. But not quite, because there will be many 0 terms inside the series as well, inside the two series. So for example, on these two examples, sigma Pn is going to be the series 1 plus 0 plus 1/3 plus 0 plus 1/5, so on. And sigma Qn will take the negative terms, will be 0 plus 1/2 plus 0 plus 1/4 plus 0. And on the second series, sigma Pn is going to be 1 plus 0 plus 1/3 squared plus 0 plus 1/5 squared, and so on. And sigma Qn is going to be 0 plus 1/2 squared plus 0 plus 1/4 squared plus 0, and so on. So first we have this important theorem that is relates these the three series sigma An, sigma Pn, and sigma Qn. So if you have a general series sigma An and you define Pn and Qn by star, then if sigma An converges conditionally, then it must be that sigma Pn and sigma Qn both diverge. And if sigma An converges absolutely, then the two series sigma Pn and sigma Qn will both converge, and the sums of these series will be related as expected, that sigma An, the sum of the original series, will be the difference of the two sums, it will be sigma Pn minus sigma Qn. The proof of this is not difficult, but I'm not going to prove it. But this theorem is needed for these two important theorems about rearrangements of terms of conditional absolutely convergent series and conditionally convergent series. So you already proved together that if when we talked about rearrangement of series, that if you have a positive series that is converging, if you rearrange its terms in any manner, then the new series will still converge and to the same sum. So absolutely convergent series share this very nice property with positive series. So here we have this, this is what this theorem is saying. This theorem says that if sigma An is absolutely convergent with some S, and if the ANs are rearranged, the terms of the series are rearranged in any way to form a new series, let's call it sigma Bn, then this new series is also absolutely convergent with and will have the same sum S. Okay, the proof of this theorem, which I don't show here, again we'll use the sigma Pn, these two nice series, sigma Pn and sigma Qn. Okay, if this is not surprising, this result would be very surprising. If you remember that we took on our first video on rearrangement of series, we took first we knew that the sum of the series is ln2, the alternating harmonic, and then we did a rearrangement, a clever rearrangement of the terms of the series by taking the first two positive terms followed by the first negative term, then the second two positive terms followed by the second negative term, and so on. And we showed that the sum of the rearranged series is not ln2 anymore, it's 3/2 ln2. So it turns out that this is like what we did here is it's not special about this series. We have this following surprising and strong result that says that if you start with any conditionally convergent series, so like the first series here, then, and I give you any number, then you can rearrange its terms in theory, can be rearranged to yield another convergent series whose sum is that number. So a number positive or negative, rational, irrational, whatever you want, I can rearrange the terms of a conditionally convergent series so that to a new series whose terms are exactly these terms but with a different order, but with sum at the given number. Moreover, it also could be rearranged, the terms of this series could be arranged to a series that diverge to positive infinity and also that can diverge to negative infinity. Again, the proof of this theorem would rely on the fact that when you have a conditionally convergent series, that the two associated series sigma Pn and sigma Qn will both diverge. I'm not showing the proof here, but it's good to know.